All right, this is day 2 of Riemann sums, and we're going to look at a more formal limit definition for these Riemann sums. So, yesterday we talked about problems like this where we can approximate the area between a curve and the x-axis using a finite number of rectangles. Like in this case, it's n equals 4. We have 4 rectangles here. We can see this is just an approximation. It is an overestimation of whatever the actual area is between this curve and the x-axis. So say this is f of x equals x squared. Write the definite integral that the Riemann sum to the left approximates. So the integral, this would be the integral from, because the rectangles stop here, from 0 to 2 of x squared dx. And we would be approximating it by finding the area of each of these rectangles and adding them together. And if you look at this, each rectangle is marked off like a half unit as its base. So 0 to 1/2, 1/2 to 1. So the delta x here for each of these is the same. The delta x is equal to 2 minus 0 divided by 4, or you can just see it visually, it's 1/2. So all of these rectangles have a base of 1/2, and then they have different heights depending on which rectangle you're on. So the first one has a height of f of 1/2. Second one is at a height of f of 1, f of 1.5, and the last one has a height of f of 2. And I'm not going to find the value for this, but whatever this is an overestimate, just an approximation of this area. How can we make this approximation more accurate? So think about this. I used 4 rectangles. If I used 8 rectangles, then I would have, rectangles that fit a little bit more. They would still be over what I need, but I wouldn't have as much of this like overestimation happening. If I could use 16, that would be even better. And so the idea is we need more rectangles, right? And ideally, instead of having a finite number, I would have an infinite number. So if we need more rectangles, we need n, the number of subintervals, to approach infinity. The reason that's more accurate is it cuts the width down. So delta x approaches 0. If you think about having very skinny rectangles here, it's like you're filling in the lines, like with little lines here, you're filling in what the area is under that curve. So if you're allowing things to approach infinity or 0, that uses limit notation. So a definite integral can be defined as a limit. So this is very fancy notation for Riemann sums. So let's break this down. First off, on this side, we have the definite integral of f of x. And this represents the area between f of x and the x-axis. Okay, so what is this on the left side? This is the formal limit definition of a Riemann sum. So this says the limit as n approaches infinity. So that just means allow us to add up infinitely many rectangles instead of just using 4 or 6 or whatever. This is called sigma notation. Sigma means add or sum all of the terms. So sum of infinite rectangles from I equals 1 to n. So what's that about? So this is saying, well, the first rectangle, like this first mark right here could be I1. This one could be, X1. This could be X2. This could be X3. This could be X4. The X's that I actually plugged in here are like X sub I. So I can go from X1 to Xn. So X1, X2, f of X3, f of X4. We could just keep going on forever and ever as we allow n to approach infinity. What is this expression here? Well, remember, delta x times f of x sub I. This is delta x. My pen is not writing. There we go. This is delta x, and I multiplied it by each f of x 1 or x2 or x3. So this expression is just the area of a rectangle. It matches over here where we have f of x dx. This is just the same thing. The dx represents the delta x. It's just saying let delta x be incredibly small, approaching 0. Okay, so what are we doing with this? What are we going to have to do for the AP test? If you really could have infinitely many rectangles, then this limit is exactly equal to, it's no longer an approximation, it's exactly equal to this definite integral. We're not going to have to my knowledge, we're not going to have to evaluate the limit, but we will need to be able to set it up or take a look at a limit setup and equate it to like what definite integral it's being set up for. So let's start with this. Based on the graph provided, write the limit definition of the definite integral represented. So let's start with what is the definite integral? They're trying to get me to go, see the shaded area, it goes from 1 to 3. And I have the function for you right here. So what I want to do is say we're trying to represent the integral from 1 to 3 of f of x dx. So let's make it 1/8 x cubed dx. And that is exactly equal to the limit as n approaches infinity of sigma from I equals 1 to n. And what is this delta x f of x sub I? This is kind of where the bulk of the problem is. We need to come up with expressions for those two things. So what is it? All right, so how do we find delta x? I meant to write this up here, sorry. How do you find delta x? Delta x is always subtracting your boundaries here for integration, so b minus a, the distance between those two things, divided by n. And f of x sub I, it's equal to, so one of these rectangles would start at the value for a, and it would have a width of delta x. And then the next rectangle would go from that spot and have another width of delta x. So like the second rectangle would be starting at a, add 2 delta x. Starting at a, add 3 delta x. So in general, you're trying to evaluate f of x sub I is f of a, where your integral starts, where your shaded area starts, plus delta x times I, because I represents which rectangle are you on? Are you on the first or the second or the third or whatever? All right, so let's calculate those two things here. So back to this. What is delta x? Delta x is equal to 3 minus 1 over n. So it's equal to 2 over n. What is f of x sub I? Well, that's always going to be f of a plus delta x times I. So the only thing that changes in each problem is what is a and what is delta x. So f of a is 1, where we're starting. Delta x was 2 over n, so let's make this 2i over n, or 2 over n times I, whatever. Okay, and then remember, we have an f. This just means plug this expression into f. So let's go ahead and write this into our limit notation again. So now it's the limit as n approaches infinity of the sum from I equals 1 to n. Instead of delta x, I'm putting in 2 over n. Instead of f of x sub I, I'm going to plug this into f of x. So let's do this. 2 over n. F of x is 1/8 x cubed. So I can say times 1/8. What's x? This whole thing. Cubed. Now, I'm going to stop this here. I could simplify it. I would not bother cubing this binomial. In years past, we have talked about, like, we would cube this binomial, and we've talked about what does this limit come out to? How do we actually do this summation? But I haven't found that on the AP test, so I don't think that that's something we need to do. If you're interested in that, come see me in office hours. We can go through it. But this would be my limit definition of the Riemann sum for this definite integral. Let's set it up again for number 2. So this time we have a different function. We have different shaded area. It goes from -2 to 2. So in general, I'm trying to do the integral from -2 to 2 of e to the x dx. It's exactly equal to the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of x sub I. I like to write this little formula out every time because it gives me something to do. Like it sets up the problem for me and reminds me what my steps should be. Next step is to find expressions for these two things. So delta x should be easy. It's always b minus a, so 2 minus negative 2, that matters, over n. That's actually 2 plus 2, so 4 over n is our delta x. F of x sub I is always f of a plus delta x times I. So a in this problem is negative 2, so f of negative 2 plus 4 over n times I, or 4i over n. I is not an imaginary number, by the way. We're talking about just a subscript. Sometimes we'll see k, but it's usually I or k as the constant there. Okay, now I need to actually plug that into the function. The function is e to the x, and I'm going to carry on with my limit definition here. So now that I know these two pieces, I'm going to sub them in here and here. So oh no, not the integral. Sorry. So the limit as n approaches infinity of the sum from I equals 1 to n of delta x, which is 4 over n, times f of this. So what is this? So e to the x. And in place of x, we're putting this whole thing. Negative 2 plus 4i over n. Again, we're not actually going to find this limit. The most we would maybe need to do with this, which we'll do on the next page, is expand out a few terms. Because sometimes they will show you a few of the terms expanded out, and you're trying to go back and find the correct limit notation. So we'll practice that too. All right, what about the third one? Now it's ln of 2 minus x. The integral, the shaded area goes, it could include negative area too, by the way. It goes from negative 4 to 2. So this would be the integral from negative 4 to 2 of ln 2 minus x dx. All right, this is equal to the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of x sub I. What is delta x? Delta x is negative 2 minus negative 4 over n. It's 6 over n. If I did it the other way, it would be negative 6 over n, which is possible, but you have to do b minus a, top number minus bottom. Okay, so that's delta x. F of x sub I is equal to f of a plus delta xi, which we now know is f of a is negative 4 plus 6i over n. And let's go ahead and put it into our limit definition here. So the limit as n approaches infinity of the sum from I equals 1 to n of delta x, 6 over n, times ln of 2 minus, what are we subtracting? All of this, so make sure it goes in parentheses. Now, you could simplify this as well. Again, I'm not expecting that we have to actually take this limit because that would require some extra summation rules to memorize. But they might simplify this and say, okay, it's the natural log of 6 minus 6i over n. All right. For our last two problems, given a definite integral, so instead of giving you the graph, I'm showing you the integral, write out the first four terms of the limit definition of the Riemann sum. I'm still going to write the Riemann sum, this thing, and then I'll expand out the terms. All right, so we're going to start with, let's go ahead and start with, we can calculate our things here, right? We can say delta x is equal to 1 minus 0 over n, so it's 1 over n. F of x sub I is equal to f of a plus delta xi. So that's f of 0 plus 1 over n times I. So it's really just f of I over n. So let's start with our limit definition here. So this integral is equal to the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of delta x. What is f of delta x? It's 1 over 3 plus, and what are we putting in for x? Just a little I over n. Okay, so here's the sum. Even though we're not really evaluating the limits, I want to show you what this means. So write out the first four terms. So you would still have the limit as n approaches infinity, but instead of having the summation, we're going to start expanding out the terms. So this just means plug in 1 for the first term for I. So it would be like 1 over n. Now, all of these are going to have a 1 over n. So when you're plugging in the numbers for I, it's really just saying like we'd have 1 over n, and then we would have, here's the first term, 1 over 3 plus 1 over n. Oops, not parentheses there. Plus, because summation, what's the next term? So now plug in 2. Still be 1 over n, so I've got that factored out here. 1 over 3 plus I changes to 2. 2 over n. Plus, we need to get 4 terms here. So I'm taking this out to I equals 4. This does continue on forever until you get out to n, I guess. So I didn't show the nth term, but the nth term would be 1 over 3 plus n over n, right? So it'd be close to like adding a 1/4 in the end. We're not actually taking this limit because, again, there are more rules to this, but sometimes they'll give you this, and then you have to go back and say, that goes with this integral. All right, let's take a look at number 7. So first let's do delta x. It's 3 minus 1 over n, which is 2 over n. F of x sub I should equal f of a plus delta x times I. So that's f of a, which is 1, plus delta x, 2 over n, and I'm going to put the I up there with it. Okay, and then we're going to write out our limit definition. So this integral is equal to the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of x sub I. So square root of 2 times 1 plus 2I over n. Because instead of square root of 2x, square root of 2, and this is the x. Let's go ahead and show the 4 terms. So limit as n approaches infinity of 2 over n times, what are the 4 terms going to be when I start plugging in 1? So here it's not going to just go 1, 2, 3, 4, because look, you would get the square root of 2 times 1 plus, if you plug in 1 for I, you get 2 over n, plus the square root of 2 times 1 plus, if I plug in I equals 2, because these are integers, by the way, I plug in 2, this becomes 4 over n. So it's actually going to scale up by 2. So I'm going to be kind of out of room here. Put in 3, 6 over n. Put in 4, 8 over n. Plus dot, dot, dot. All right. Our homework tonight is an AP Classroom, just to practice these. These are usually multiple choice problems so far. I have not seen them often on free response. This is kind of tricky stuff because it's pretty abstract. So I just wanted to make sure we practiced it a little bit before we move on to the bulk of what we focus on, which are not these types of Riemann sums.